So today we're going to talk about return-oriented programming. So in order to talk about this, we have to kind of do a little bit of refresher on assembly and some stuff like that. So bear with me. The first, I don't know, little bit's going to be a refresher, but it'll be worth it because then you can understand the second part where it's all really cool, right? So just remember that, you know, your data types, a char is just a byte, you know, and then short is 2 bytes, and you know, keeps getting bigger and bigger from there, just doubling. But we're going to be doing a lot of stuff in assembly, and you're going to be seeing a lot of, you know, hex and all that stuff. So we're going to just go through all this really quick. Remember the conversions. You guys all know this, so I don't know. I was expecting some other people maybe to be here that hadn't done this kind of stuff before. But yeah, I think you guys all know hex conversions. But
You know hex conversions?
I
They don't have
don't.
hex conversions.
you don't? Okay, never mind then. Sorry.
I mean, it makes
I won't
sense.
assume.
It just converts sideways. So.
Yeah. So hex is base. So we have base 10 counting system, right? You know, 1 to 10. You know, binary is just base 2, right? So there's just 2 options. Hex is base 16, so it goes, you know, from 0 all the way up to F. So once you hit 9, you don't go to 10, you go to A, B, C, D, E, F. So when we look at, you know, almost anything in like a disassembler, or like when you're looking at memory and stuff like that, it's all in hex because it's a lot easier to summarize binary in hex instead of just a bunch of 1s and 0s, right? So these kind of conversions should be pretty familiar once you start doing, you know, once you start looking at a lot of disassembly and assembly and all that kind of stuff. But so we're going to be looking at a lot of hex today. Just another quick refresher on architecture. There's CISC versus RISC. So CISC, Intel is CISC, and it means it's a complex instruction set computer, which means that there's a lot more instructions. So like move and push and pop and add, those are all instructions. And in Intel, there's a bunch. I mean, if you look at like the actual Intel manual or whatever it's called, it's like this big. I mean, pages. It's a book like this big. It's just a series of volumes, and there's like that many instructions that the computer knows how to handle. It's insane. But when you go to something that's RISC, it's trimmed down to like the bare minimum. And so the reason why they have CISC is because it runs a lot faster when they have these really specific instructions. When they have a ton of instructions, they have really specific ones that are used in specific types of decoding or algorithms or whatever that make it run really quickly, but there's a lot more overhead because the CPU needs to know how to handle those, right? And also they're variable length instructions. That's important because that means that, you know, you can have a jump, you know, the jump to a certain address is like literally, you know, the jump command is like 2 bytes or whatever, and then the address. So that could be like a total of 6 bytes, 4 for the address, 2 for the opcode. But you know, an add instruction might be like 2 for the opcode, and then like the source and the destination, and like it might be more, right? And we'll see that once we get into some instructions later on. So RISC is all the same. It's not variable length instructions, so everything is the same, and that's helpful for stuff that it requires like specific requirements in order to run, like embedded systems, right? They don't have a whole lot of memory. They don't have a whole lot of space, or they need to be produced cheaply, so the CPUs can't have all of these instructions. They can't support all these instructions. So there's a difference there, and we're going to be dealing with i86, which is Intel, 86, which is the 32-bit architecture. So that's what we're going to be looking at today. You can do return-oriented programming in 64-bit as well, but we're just going to do it in 32 because it's a lot easier to learn that way. And then we're going to also be dealing with endianness. So there's big endian and little endian. So RISC architectures are usually big endian, which means that the way you read it, so like if you had the number, you know, 1, 2, 3, 4, 5, 6, 7, 8, then it would just be straight up 1, 2, 3, 4, 5, 6, 7 all the way up. But if you were doing it in little endian and you had 1, 2, 3, 4, 5, 6, 7, 8, you split it up into the bytes, and then the bytes are in reverse order. So you take the last byte, the least significant, and that makes the first memory address. So we'll see that later on, and I'll point it out, but just kind of keep that in mind. All right. We're going to be doing a lot with registers as well. So if you're, from learning assembly, there's plus the EIP, the instruction pointer. So a register is just a small storage space. It's usually like really close to the CPU. It's super fast. I think it's maybe even in I don't know. I don't think it's like on the CPU, it's like right next to it. But so EAX, there's some general conventions for when to use specific ones. EAX is used for return values. So if you call a function and it's supposed to return a number or whatever, that's going to be an EAX. So whenever you come back to the previous function that called the function, EAX is where your return value is going to be. It's also the accumulator. So if you're going to be adding things or subtracting things, the result is usually stored in EAX. EBX is used for the base pointer to a structure. So like if you have an array, arrays in memory are literally just like contiguous pieces in memory, right? So like if you have an array that has black, white, red, green, those strings, the first indice in the array is going to be black, right? And the second one is going to be white. So the base pointer is going to point to the front of the array, and then the way you get to something in that array is you take the base pointer plus the offset into the array. That's how they do it in assembly. So the base pointer is going to be usually stored in EBX. ECX is for counting for loops. Kind of helps too because like they try to name it. So EAX accumulator, base pointer, BXC is counter for like loops and iterations and stuff. And then EDX is used for I/O. So when you have when you're dealing with I/O. ESI is the source. EDI is for destination if you're doing like copies and stuff, like the source pointer and the destination pointer. EBP is the base pointer for your stack frame, and then ESP is the stack pointer for the stack frame. And I'll show you that in a minute too when we get to some code. Okay, so this is just simple, hello world in C, and that converted into assembly. We can see the hello world string is stored down here in the data section. So there's different sections of an executable. So when you write it in C, it's a .c file, right? You put that through a compiler, and then the compiler goes and it takes the libraries and stuff. So we're including stdio, right? The compiler goes and takes all the libraries, and it takes everything that needs to be there for the program, so it knows what functions you're calling and stuff. Puts it all together, and then it puts it into a single executable. And then when you run that executable, that whole thing is loaded into memory, right? So in memory, you now have the standard C library. You also have stdio because that's the one that we loaded in, right? So those two libraries are going to be in memory, and then our program is going to be in memory. And this is our program in memory. It's really short, but the text section is going to be where the actual code. So like the printout, hello world, the printf, like that is the code that we wrote, right? That's going to be in the text section. The data section is going to contain your variables and stuff like that. There's other sections too, but just that's what this is. That's what this is doing. So your string is going to be down here, and then it's got the length of the string right below it. And these are just labels, and when you can refer to labels in assembly, and you'll be able to pull that in later. So first thing they do is they get the length for the string, and they store it into EDX, sorry. And then they store the message into ECX. They put the number 1 into EBX, and they put the number 4 into EAX, and then they do what's called an interrupt, and they do int 80. Okay, so this is kind of something that we need to be familiar with. This is the way that assembly does a function call. Okay, so if you have a function and so for printf, for example, right? Printf is a function, and we're passing an argument to printf, right? Just one argument, but we're passing an argument. When you pass arguments, the way it does that in assembly is it puts it into registers. So if you have two arguments for a function, it's going to put those arguments into EAX and EBX. It just goes A, B, C, D, A, B, ABX, oh my gosh, EAX, EBX, ECX, EDX. It's going to go down those 4 registers for the function, or for the parameters for the function. So it just so happens that in order to do printf is a system call. So if it was a normal function, it would just push that one parameter into EAX, and then it would call that function. But because printf is a system call, it's not just a normal function. The code for printf lies in the kernel space in the operating system, right? The code for printf isn't accessible by any user. It's only accessible by the kernel. So in order to do a system call, you have to set up all your registers, and then you have to do int 80, which is say you interrupt and say, kernel, come and get me. I have something for you. Okay. So I have the table right here, just the first couple of them. So these are the system calls, and you can see in EAX if you have 4 in EAX. I'm sorry. Yeah, right. We're doing syswrite because we're printf. We're doing printf. We're trying to write. So that's why we're putting a 4. We're putting a 4 into EAX right here, right? So, anyways, basically, in order to do a system call, you gotta load up EAX with the directive for the system call that you want to call, and then you have to put whatever else needs to be in there. So, for the write function, we see we have to have 4 in EAX. EBX has to have the pointer to the string that we want to print, and then there's going to be an integer in ECX and an integer in EDX. One of them tells you, I have it on the previous slide.
You're on the wrong line, I think. You were doing sysopen.
Oh, you're right. So the int comes first, then comes the char. Yeah, okay, so int tells you where you're going to print it. The char star is going to be the actual message, and the size t is the length of the message. Thank you. And it says that here in the comments. So we have the length, we have the message to write, the file descriptor, so that's telling it to put it to system out, to standard out. That's what 1 means. If we were to put 2 there, it could, that could mean standard error, or 3 could mean to a socket or whatever. So like you can just that's how that works. And then 4 is the system call number, and then we do int 80. Okay. And then right below you can see we do it again. We move 1 into EAX and we do int 80 again. And if you look at the first one, that's the exit system call, right? So that's like the whole program right there in assembly. Now that we have that taken care of, we can move on to what return-oriented programming is. So with a typical function, or a typical program, your instruction pointer is what dictates the flow of the program. Whatever the instruction pointer is pointing at, it's going to run that instruction, right? And after an instruction is run, it increments the instruction pointer to the next place, to the next instruction, right? So that's just something that happens by default in x86. So again, they can be variable length, so you can see instructions can be different lengths. And then, it's just incremented. What we do with ROP, though, with return-oriented programming, is we don't use the EIP, we use the stack, okay? So we have to somehow hijack the stack and use the stack to try and control the program flow. We'll talk about how that works in a second. But if we can get the stack, if we can get control of the stack, then we can essentially take control of the program. The program wanted to execute, line 1, line 2, line 3, line 4, but we're going to say, actually, I'm going to cut in and I'm going to say, I want you to run over here and run my stuff instead of running what you were going to run. But there's a problem when we're trying to run commands off the stack doesn't increment automatically after we run an instruction unless a return statement is hit, okay? So that's like the whole basis of what return-oriented programming does is, oh man, I gotta explain the stack first. But essentially we're gonna run a little piece of code and we're gonna hit a return. And that return will increment the stack pointer. And then the next thing that's on the stack is gonna be another place to go and run some code and then hit a return and it'll increment the stack pointer. So it's essentially like we're trying to run instructions, but from the stack, okay? Now, how do we get control of the stack? That's through a buffer overflow. And that's the next slide. So first, just want to point out the stack, right? So earlier we were talking about the EBP. It's one of the registers in the ESP. This is the base pointer, and this is the stack pointer. So this right here dictates the current frame for the function that we're in. So let's say that we called this verify pin function, okay? And it sets up the stack. And this is the stack frame for the verify pin function. These don't actually match up. I got these separate, but it just, this is kind of generic, so we'll kind of adopt it to what we need it to be. When we call a function, there's a prologue and an epilogue. The prologue, typically, you're going to reset. So like let's say that we're in this we're in this stack frame, and we call another function. So we want to make room down here for the next function stack frame. So the first thing that we do is we're gonna push onto the stack the location of the old base pointer. Okay. So here, and we're gonna save it down here, and then this is gonna come down and be pointing down there now, right? So this is gonna be down here. This is gonna be right here, and then the next thing it says is to move EBP into ESP. So that says we're gonna take EBP here and just move it all the way down here, right? And then the next thing is we're gonna subtract some number from ESP. That number is determined by however many local variables there are in that frame. So in this frame, there was 1, 2, 3, 4 local variables. So 4 times 4 is 16. If these were all ints, we would subtract 16 from the stack pointer, and that would get us here. So in our example, since we're down here, we brought the base pointer down here. We're going to subtract 28, so the stack will grow 28 hex down, and that's going to be our new frame pointer. Okay, does that make sense? And then when we're done with the epilogue and the return statement, we're going to basically do the opposite, and we're going to like move the stack back up, and we're going to pop. So if we move the stack back up here, the thing that was right here was the old base pointer. So if we pop from right here into our base pointer, that's going to say move the base pointer back to where it used to be. Does that make sense? Because we saved where the base pointer used to be. So it's like we created this frame, we're going to delete it, we're going to pop it, and then we're now back up to where we were. So it's just creating a new frame and going back to the old frame. So something that I didn't mention there is that right before all of that takes place, as soon as you hit a call statement, right? So if we're calling a function, we're going to calling a function is essentially, we're going to now create a new stack frame, right? We're going to go to a new chunk of code, and we're going to need a new stack frame. But we need to know how to get back to where we were. So this call, what happens underneath is it takes the next address after the current instruction, and it pushes that onto the stack so that it can know where to go back to. So that's this return address, right? So let's say when we call verify pin, let's say we're in main. Okay, this is main. We call verify pin. We're going to push on the return address so we know how to get back to the instruction right after verify pin was called. And then we're going to do the prologue. So we're going to save the base pointer. We're going to subtract the stack. We're going to do the whole function. And then at the epilogue, we're going to delete it, come back. And then right here, we know how to get back because we're going to pop the return address into EIP. Okay? Does that make sense? Like when we're shrinking the stack, right? We've got this stack frame, and when we do the epilogue, we're going to come up here, we're going to pop the base pointer, and then this will be pointing at the return address. So if we pop again into EIP, then whatever this return address is going to go into EIP, and we're going to start executing from there. Okay? That's the whole idea of taking control of the stack, is we're going to try and overwrite this return address, because if we can overwrite this return address with our own address, then when this gets popped into EIP, we can tell the program to go anywhere we want. Okay? So that's what a buffer overflow is. Buffer overflow says, let's say I create a 1, 2, 3, 4, 5, 6, 7, 8. Let's say I created an 8 byte long variable. What happens if I put 10 bytes of data into that, right? Or 9 bytes of data, right? We're going to overflow the buffer unless we check. So some programming languages check. C doesn't check. So we can put as much data as we want into that buffer, and we can continue to overwrite it. If we overwrite it, we're going to overwrite data that used to be there, right? So there's a 0, 3 here. If we write excessive, this 0 is the null terminator after to tell the computer that the string has ended. So we're going to overwrite those 2 bytes with E and 0. So what we can do, let's say that ZZ here is a buffer of only 8 bytes. So the program thinks it's only going to take up this much space, but if I put in 12 bytes, I'm going to overwrite up to here, and if I put in 16 bytes, I'm going to write over here, and if I put in 30 or 24 bytes, 20 bytes, I'm going to overwrite the return address, right?
So it would overwrite up on the stack instead of going down?
Yeah, that's how the stack works. I don't know why, but it does. So it's because the stack is weird. So here's low memory addresses and there's high memory addresses.
It grows down.
It grows down, but when you write to it, or when you have like, so imagine that the stack pointer is actually pointing right here, because these 8 bytes, because it grows in the memory addresses grow, right? So let's say that this was memory location 200, right? This would be 2001, 2002, all the way up to 2008, right? Or 208, I'm sorry.
Oh, right, because you're subtracting off of it.
Yeah, so if this was hex 20, this would be hex 208, and that would be the beginning of the next thing, right? So if we were to start writing into that, it's going to write increasingly, right? And so it goes up, and we're going to overwrite that return address. So this is kind of how buffer overflow works. If we have a variable here and we write a lot of data, we can overwrite the rest of the stack plus the old base pointer and even the return address. Okay, if we override the return address with the specific address, I mean, yeah, maybe it's garbage. Maybe we just put in a bunch of letters. It's not going to do anything. But if we put in a specific address, we can tell it to go wherever we want it to go. Okay. So using a buffer overflow, we can take control of the stack, and essentially we can take control of the instruction pointer because we can tell it where to go. So like we said with return-oriented programming, we're going to put a bunch of instructions on the stack. But they're not actually instructions. What we're going to put on the stack is we're going to put locations in memory where instructions that we want to be run are located. Okay, so with a typical buffer overflow, you put your shell code, you put actual code onto the stack, and you try and run that. So if you have shell code and you can upload that onto the stack and you can run it, then you got a shell and you're good to go. But modern operating systems have been able to, I mean, like, buffer overflow has been around for a long time, and they've been a really big problem. So they've started to try and create ways that buffer overflows won't work. One of those ways is called DEP, data execution prevention, which means that there's certain portions of the executable. Remember when we had we have the text section and the data section, and there's other sections. Only certain sections of the executable are executable. So the data section is not executable. The stack is not executable. So if we put actual commands, actual instructions onto the stack and try to run it in a modern operating system, it'll fail and say, someone's trying to hack you because they're trying to run stuff off the stack, and normal programs don't run stuff off the stack. They only run stuff from the text, locations and strings and stuff like that. So, so we can't actually put instructions. That's a typical buffer overflow, but a return-oriented programming exploit, we put gadgets. We're looking for gadgets. We put memory locations of code that we want to go to, okay? So a gadget is like, usually they're really short, like pop EBX, return. That's a gadget, right? And so when, yeah, so basically, if we can find enough of these really short snippets in already existing space in memory, then we could actually build our program, right? Like with that hello world example, there was like, move the length into, I think that's the next slide. Yeah, this one. So with this hello world example, we have these commands: move length into EDX, move message into ECX, right? Move 1 into EBX, move 4 into EAX. If we can find places where commands like that are already existing in memory, we could essentially write this whole program by just saying, go here in memory. And if you go here in memory, it'll move some number into EDX, and then it'll return back. And then I can say, okay, now go here in memory. And it'll go over here, and it'll say, all right, move some string into ECX. And then it says return, and it comes back, and it says, oh, okay, now I want you to come over here in memory, and it says move 1 into EBX and come back. So we're not actually putting any instructions on the stack. We're just telling it to go to random places in memory that we found that have the instructions that we want to run. So, yeah.
So how are you changing the instruction pointer to do that?
Because of the buffer overflow, right?
So you're not overwriting the data, you're just overwriting up to the instruction pointer?
Yeah. So if we can overwrite this return address, let's say we overwrite it with some place in memory, that says move 5 or move. So the actual length of the hello world string was like 12 or 13 characters or something. So if we can find in memory somewhere that says move 0e, that's the number for 13 in hex, move 0e into edx and return. If we can overwrite this with that location in memory, it'll just go and do that for us and then come back. Right. And because it had a return statement after it, it'll increment the stack pointer. Say we have another address right here, because we can overwrite as much as we want, right? So we're essentially just going to slap on addresses in memory that we want to go to that are going to run the code that we want it to run, right? And it's just going to keep going and execute each one of them. So the trouble now is that we have to find all these little gadgets, right? So there's this really cool program called ROP, Exploitation Made Easy, I think, is what it stands for. Huh?
Looks like a rope to me.
Yeah. It's on GitHub. I just downloaded it and it works. I mean, I had to like install an extra package or something, but it works right out, pretty easily. And you basically just load in a binary. So I gave this libc, the libc binary, and I said, go through the whole binary and index all of the instructions in the libc binary so that I can search them. And I can say, search for move EAX. And the question mark means that it follows with the return statement. Look right here. Move 4 into EAX, and then this double semicolon just means return. So move 4 into EAX, that's one of our instructions right here, right? So we know that hex A7820, that's an offset. So that far into the libc binary file is this line of code. Move EAX, move 4 into EAX, and then return. So if we can calculate the beginning of libc and then add the offset, that's the address of move 4 into EAX and then return, okay? So we have to do that for every single command that we want to run. So, we can go ahead and we can, so in order to do it with the string, it's a little bit different because the string hello world doesn't already exist somewhere in memory, probably, right? So if we wanted to make that, then we have to go through some extra stuff. But we know that the length of hello world is 0e because of HU, and if you count it up, I think it's like 13 or 14 or something, whatever. So if we already know the length of it, then we can just find somewhere in memory that it says, move 0e into EDX and return. So we go find that gadget, we calculate the offset, and we grab that memory address, and that's the first thing that we need to run. Second thing we need to run is worrying about the string. So the cool thing about this is that we're basically like, we're making our own stack, right? So we can put an address on, we can put another address on, we can even just put in some text, right? So if we put on hello world right here, and then, so this whole thing is our stack, but it's flipped. So imagine that our return address was right there up at the top, and then there's another address here, another address, like right, if that makes sense. So the first address is gonna do that. The second address is gonna go somewhere in memory that has pop EAX followed by a pop ECX and then a return. So if we tell it to pop, it's gonna pop off of the stack, and we're on the stack, right? So it's gonna look at the next thing on the stack, and it's gonna pop hello world into EAX. It's gonna pop the next thing, which is this memory address that we give it, into ECX, right? So if you remember from the hello world thing, the string is written in .data, typically, if you were to write the program the real way, right? So I found the address where the data section starts. That's what this address is right here. So I'm basically telling it, grab this string and put it in EAX, and then grab this address, which is the beginning of the .data section in my executable, and put that into ECX. And then I'm going to tell it to put whatever is in EAX, which is the string, into the address, into the place that is pointed to by what is in ECX. That's what the brackets mean, remember, from assembly. If we just had it without the brackets, move EAX into ECX, we would just copy hello world into the ECX register. That's not what we want to do. We want to put hello world into this memory location, right? So that's what the brackets mean. So we're saying, set me up with the string, set me up with the place I want to store it, and now just move it into the place I want to store it, which is this memory location. And then it'll write it into the .data section, okay? then we need to put a 1 into EBX, and we need to put a 4 into EAX, and then we call our interrupt. So it's funny because this whole time we haven't actually written any code. We've just set up our registers to be like we were running a program, like we were running this code, right? So the program, or like the CPU doesn't know any different. When the kernel gets the interrupt call, it's just going to look in the registers and it's going to do what it needs to do based on what's in the registers. It's going to look in EAX. There's a 4, so it's going to do assist write, and it's going to look in the other registers, and they're all filled out properly. So it's going to go ahead and write print world for us, right? So we just did a ROP for print world, or printf hello world, and that's not very malicious or fun, right? So this is what I was talking about with calculating the offset. So so I have my program is called ROP NSP, and then I have it run. I'm running it in GDB right now, and if I do a PS aux, I can find out the PID is 8111, and then if I cat out the memory maps from the proc directory on the 8111 process, then I grep for libc, I can see exactly where the executable portion of libc resides, right? Does that make sense? So that is the base address for the executable portion of libc. And then using that rope me program, I can search for move EAX, and we wanted move 4 into EAX. So we get that offset into libc, add it to the base address of libc, and that gives us the actual address of that move 4 into EAX return.
Wouldn't the beginning of that lib library be different on other systems though, or does it?
Yeah, it would.
So how do you find that on a system that you?
So
because you don't have a bash, so,
right. So it'll actually be different on the same system when you run the program again in a minute, because of something called address stack layout randomization or something like that, ASLR. And that's something else. So DEP was one thing that they've implemented to try and stop buffer overflows. Another thing was address randomization. Because if you can't predict an actual address, it's a lot harder to do this kind of stuff.
Right.
So that's true. And there are ways to try and figure that kind of stuff out. So if you have a different exploit that leaks the memory address of some function, like if you can find the memory address of the exit function or the printf function, using a different vulnerability, you can say, okay, well, I know that printf is some offset into libc, and so because I just found that address, now I know the offset into memory where libc starts. So you have to couple it with another exploit in order to get this kind of thing to work. But ROP by itself helps you get around DEP. You have to do some other stuff in order to get around ASLR and stack canaries and stuff like that. But
the same thing.
Same question. Yeah, great. Right. So we did it with Hello World, but what if we did it with something a little more interesting, right? So this is the thing that I was trying to get working, and I really wanted to get it working so I could show you guys, but I couldn't figure out why. I tried to turn off ASLR, and I tried to do all this stuff so that I could get it to work, and for some reason I couldn't get it to actually work. But I understand how it works, so I'll just try and explain that. So so we were going to try and put hello world into the data section, right? But what if we were to try and put the string /bin/sh into the data section, right? The reason why there's 2 slashes on sh is because you want to write 4 bytes at a time. And so not 4, 8 bytes, or yeah, you want to write 8 bytes at a time. And so so /bin is going to be, it's 2 bytes per character, so 8 bytes. And then /sh would only be 3 bytes. And then there would be a null byte if we were to try and make it a 4th. And we don't want to have any nulls. So the way that C works is with strings, it goes until it hits a null character and then it stops. That's how strings work in C. So if we made this really if we added all this stuff together, I mean, I'll show you in a second. But basically, if there was a null byte in our exploit anywhere, then when we try to give it the program our exploit, it's going to stop right at that null byte. So if there was a null byte right here after the sh, it's going to stop right here and not get anything we put after it. So we have to fill it up so that there's an actual null byte. So anyways, so let's just walk through this and see how this works, okay? So the program that I was trying to do this with had a buffer that was that was 256 bytes long. All right. And if you remember from our stack, so let's say that this is my buffer and it's 256 bytes long, right? There's this saved EBP right here. So add 4 bytes is 260. So 260 would get us all the way up to this return address, right? Does that make sense? So we're going to fill up our buffer and the old EBP with just garbage, with just A's. So 260 A's. And then our first ROP instruction. Our first instruction is going to say pop into ECX and pop into EAX and then return. So it gets the next thing on the stack because we're popping into ECX. So we get the next thing on the stack and we put that into ECX. Okay. So the string to be popped into ECX is /bin. The next thing is popped into EAX is the address to be popped into EAX to write bin to. Okay. So this was somewhere in the data section, remember? So we're going to pop bin into ECX and we're going to pop the address of someplace in the data section into EAX, and then we're going to do that tricky move thing again, right? So we're going to move bin into data. And then we're going to do the same thing again with the SH, and we're going to put it right behind it. So if you notice the address right here is offset by 4 bytes. So we're going to put the /bin, so that's going to be at 9704, 9705, 06, 07, 08 is going to be where we're going to have //sh. So we're just putting that contiguous in memory. Oh, thanks. And then what do we do? Yeah, so that's what that address is. So yeah, you can see it's the address from up above. That's actually the wrong one. See, I don't know why it says that. Never mind. Anyways, and we're going to do the move thing again. Now, we have to do something tricky because remember how I said we can't have null bytes? Well, we have to have the string. We have to have the string bin sh end in a null byte. Otherwise, when we try and read it later, the program's going to read, and if there's no null byte after sh, it's going to keep going. And if there's other stuff after sh, it'll grab that until it hits null byte. And if it tries to run that as our shell, it's not going to do anything, right? So we have to put a null byte at the end of it. And the way we do that is we create a null byte by zeroing out one of the registers. If you XOR anything with itself, it'll make 0. So if we XOR EAX with EAX, it creates 0. And then we can take that 0 and put it into memory right after the string. Okay, so that's essentially what we're doing there. So we're creating 0, we're popping the location where we want to put it into memory, and then we're doing the tricky move thing again. And we're putting the 0 right behind bin sh. Okay. Then I actually forgot to put this into the slides. Let me show you. Oh no, I did. I just forgot it's in here. So the command in C to spawn a shell is exec CVE. Okay, so if you were to be writing a program and you type exec CVE as a function, you have to pass it in the string bin sh. Essentially, exec CVE is executing a command in a shell, right? Or it's interpreting it as a command for the computer, right? So if we pass in the string bin sh to exec CVE, it's going to spawn a shell, okay? And the parameters that it takes, it doesn't take parameters in the normal EBX, ECX because there's actually too many of them to fit into this many registers. So the first one actually just points to a structure that has a bunch of different things in it, okay? But turns out most of those things don't actually have to be set. So if you remember when we were talking about earlier with arrays, a structure is the same thing as an array, okay? So if we had an array that starts right here, the first thing is going to be the first thing in the struct, the second thing is going to be the second thing in the struct, third thing is going to be the third thing in the struct, except it's just growing down, right? Because it's a pointer. But if we just add 4 to the pointer, we get to the second thing in the struct. So it turns out that most of the things in the struct don't actually have to be set. So we can call it with actually only a couple things. and we can still pop a shell. So what we're going to run it with, so one of the things you have to put in is the environment, the pointer to the environment and the pointer to the arg, like argv, pointer to the arguments. So those are 2 pointers that we have to pass in. And then bin sh. So it's going to be bin sh, environment pointer, and then I think the opcode right here is into EAX, yeah, because that's 0B, right? And 0B is 12 or is 11. And so EAX with opcode 11 is exec CVE, right? So, sorry, I didn't organize it very well. You got to keep going through them. Yeah, okay. So basically, we set up our string in data. We put our argument or whatever, our pointers to the argument, pointers to the environment into EDX, ECX. EBX is going to have the pointer to the string bin sh, and then EAX is going to have the directive 14 or 11, so that when we call the system call, the kernel knows to do an exec CVE. Yeah.
The double slash, that's not gonna.
It doesn't actually matter.
It just ignores it. You can put
Yeah, you can do it. You can do
it.
it in a shell. It'll still work.
Cool.
Yeah. So that just fills up that null byte that we didn't want to have. So turns out there aren't any interrupts in libc because libc is already kernel stuff. So we have to do a system call a different way, and that's using this call GS syntax, but it's essentially the same thing as an interrupt. So if we were to put all of this onto the stack, it would look something like this. This is a picture that I found online that actually isn't, like, I didn't want to go ahead and make all of this, so it's basically the same thing. So they're doing kind of the same thing, and the resolution is really bad. I'm sorry, but it would have just taken me so long to draw all those arrows and stuff in Paint or something. So anyways, so they've got their bin sh up there that's null terminated, which they've got on the stack, so it doesn't matter, but we didn't want to, we didn't want to have a null in our thing, so we had to do it a special way. But so we've got, pretend that bin sh is in data and it's not actually on the stack, right? So they're going to do the exact same things that we did. They zero out a register so that they can create a null byte. They pop ECX and EDX into, so they're going to take the next 2 things. They're going to pop those into those registers. They're going to move. This is a little different syntax. So instead of moving here into here, they're going to move here into there. So they're going to move EAX into an offset from EBX or EDX, which is essentially trying to store the string like we were doing. Then they're going to set up the EBX register. They're going to set up the EC and the EDX register. And the EAX register was already set up, I think, from earlier. And then they're going to do their call GS thing, right? So that's how our stack would look after we did our buffer overflow, overwrote the return pointer with this, our first gadget, and then we just had a bunch of gadgets and stuff on top of it. This is what it would look like. And when the program tries to pop that, that return address into the EIP, it's going to hit our gadget, and it's going to do exactly what we want it to. And then it's going to return, so it's going to increment. It's going to do exactly what we want it to. It's going to return, it's going to increment, and it just does exactly what we want it to do. So that's how return programming works. We already touched on a couple of these things, but why would we need to use ROP, right? So there's some protections that have been put in place to try and stop buffer overflows, and that's ASLR, I think it's address stack layout randomization, and the data execution prevention. There's also canaries. You guys have heard of canary in the mine. Like if the canary dies of lack of oxygen, the canary will die before the miners will die. And so if the canary died, then miners knew they had to get out of there because their oxygen was gone and they were going to die soon, right? So a stack canary is on the stack right here, in between the actual local variables and all the important stuff up here. They put just a random number, right? And the program knows what random number it puts in, but we don't know what random number it puts in. And before it tries to return from the current pointer or the current stack frame, so when we did that stack deletion fun stuff, before the program starts to try and do that, it'll check the canary. And if it's been tampered with, it says, whoa, someone's messing with your stack. You do not want to return right now because you don't know where you're going to go. So yeah, so that's what a canary is. And there's ways to get around that, but you'd have to account for that with ROP as well. So ROP isn't an end-all be-all solution, but it is pretty cool, and it helps you get around data execution prevention only, because you're not executing from the stack. You're just going into random places in memory and having that stuff execute and then come back to your stack, right? So there's certain systems and, like intrusion detection systems and stuff like that that can try and like determine if code is good or bad based on what, if you try and like upload a program that has exec CVE bin bash, oh, this is probably malicious code. Don't put it on your system, right? Programs that try and detect what code is there won't work against this, because all it's going to see is a series of jumps to other places in memory, which is totally something that code does anyways, right? So it's not going to know that that's bad code. So it totally just gets by that kind of detection. So code injection isn't necessary anymore. We don't actually have to put code onto the stack. We can do it by building our own code through jumping around, right? Compilers like complicate the heck out of stuff to try and save on cycles, to try and like, do things more efficiently. Like there's all sorts of optimizations and stuff that compilers do to try and make code run faster. And because of that, our jumping around looks totally normal. It's not weird at all. So thanks to compilers, right? And then antivirus stuff, like kind of like what I was talking about earlier, if it tries to detect certain pieces of your program, it's just going to totally not be able to recognize that because you don't have any actual code in your exploit. Furthermore, it makes reverse engineering really difficult because let's say, you saw our exploit. This is our exploit. So I have all these pluses here because literally if you were to just take like all these strings and stuff and put them together, that is the exploit. That's what you would submit to the program to be your like input. So like, if you were to like do / the program name, and then like if you're supposed to try and put in something on the command line, if we were to give it this big long string, that's our exploit. Okay, that's all it is. It's just a bunch of addresses and random stuff that is so perfectly constructed that it knows how to take over the computer, right? And if someone's trying to reverse engineer our malware, they're just going to get a series of random locations in memory that don't even exist when the program isn't running, right? So if they're trying to static analysis our exploit here, they're not going to be able to know what it's actually doing because they don't know what that address is. Like if they try and go to B7EE2AA8, it doesn't exist right now because there's nothing running. This is the library, right? libc is loaded into memory when you run the program. So if the program's not running, this doesn't exist. So you can only do live analysis on this kind of malware. You can't do static analysis. So that's another like benefit.
So you wouldn't be able to trace anything at all, right? Because
you have to run it to trace it.
Yeah, and to do that, because of that randomization thing, that would change the address of where it's at, right?
Mm-hmm. Yeah. So yeah. Anyways, makes it really hard to reverse engineer and really hard to figure out what they're doing. So, anyways, do you guys think ROP is cool?
Yeah.
I do. Anyways, that's it.
Thank you.
Were there any other questions?
I had a question.